welcome back to Chapter 9, Momentum, Part 2. So now we're going to start talking about conservation of momentum. So conservation of momentum occurs during a collision when a system is isolated. So within a system, if I can say that that system is isolated. So for example, if I have two objects and I am paying attention to only those two objects and I ignore all outside forces. So like ball versus pen in the air, ignore all outside forces, pew! Then I can say there is conservation of momentum. Effectively, momentum is always conserved within an isolated system. So then the key is setting your system so that it is isolated, ensuring that you have all parts of the isolated system within the things that you're calculating. When that's true, the momentum at the beginning has to be equal to the momentum at the end, or initial momentum is equal to final momentum. So let's assume that that's true and do a little sample problem. Two ice skaters, Sandra and David, stand facing each other on frictionless ice. Sandra has a mass of 45 kilograms, David a mass of 80 kilograms. They push off from each other. After the push, Sandra moves off at a speed of 2.2 meters per second. What is David's speed? Okay, so this is an isolated system. Sandra and David are the only two things. There's no friction, it's frictionless surface, so we're good there. So at the beginning, they are both standing still. So momentum at the beginning is 0, right? They're both at rest, so there's no velocity, so there's no momentum. And that has to be equal to the final momentum, which is equal to the mass of each of them, their own momentums in opposite directions. So that would be the mass of Sandra times the velocity of Sandra, plus the mass of David, the velocity of David. However, because they're pushing off from each other, well, let's just do it that way. Now, since they're both equal to 0, I could also say that the mass of Sandra times the velocity of Sandra is equal to the negative mass of David, velocity of David. Okay. So when I calculate and plug in, Sandra is 45 kilograms and her velocity is 2.2 meters per second equals negative 80 kilograms times David's velocity. And that's what I'm solving for, David's speed. Speed, not velocity, so direction's not going to matter. Then when I solve that out, I find that the velocity of David is 45 times 2.2 divided by 80, 1.24, but all of my numbers are in 2 digits, so 1.2 negative 1.2 meters per second. However, I'm asked for so basically I know that David's going the opposite direction that Sandra was. Sandra's going faster, David's going slower, because David's larger, Sandra's smaller. But it asks for his speed, so I don't need to worry about that negative sign. I can just say that his speed is 1.2 meters per second. All right, so let's look in a collision. So what if the things are not standing still at the beginning? Well, we can set objects in a collision so that their momentums are equal to each other before and after a collision. So I've coded before as red, and I'm using I for initial, after is blue, and I'm using F for final. And then I have the momentum of each object. So over here, object 1 is green, object 1 is green. Object 2 is purple, object 2 is purple. So I've got the momentum of the first object before the collision, plus the momentum of the second object before the collision, equals the momentum of the first object after the collision, plus the momentum of the second object after the collision. And I'm using multiple subscripts to just designate second object after the collision final. Okay, so when we define our system, choose the system that will conserve momentum. All right, with that in mind, And that's a big important equation, just by the way. There's not just for fun rainbow colors that I did all that color coding. That's a good equation to remember and use frequently. Set all the momentums up and then set them equal to each other. Before is the same as after because momentum is conserved before and after a collision. Stop and think. An explosion in a rigid pipe shoots 3 balls out of its ends. A 6-gram ball comes out of the right end. A 4-gram ball comes out of the left end with twice the speed of the 6-gram ball. From which end, left or right, does the third ball emerge? Ooh, okay. So let's draw this out. I have my pipe here. Okay. And out the 6-gram comes out the right. Okay, so over here, I've got a 6-gram ball moving with a speed of 1. Then out the other side, the left side, I have a 4-gram ball moving at a speed of 2. So 2 velocities, and this one was just 1 velocity. And then the question is, which side does the other ball emerge from? Well, so far, I know that the momentum has to be conserved in total. All the balls started at rest inside. So this one so far has a grand total of 8 velocities times masses units coming out that side. This one has 6 velocities times mass units coming out. So right now, my right side has less momentum coming out than my left side. In order to make it balance, ball number 3 has to come out of the same side as the 6-gram ball, right? And it should come out with a ratio of 2. Now, I don't know how massive it is. It doesn't give that information, so I can't tell you the speed. But I do know that it will come out the same side. So the side it comes out of is the same as the 6, which is the right side. Great. All right. Now we're going to introduce an inelastic collision. So an inelastic collision is a collision where objects stick together and hold with a common final velocity. So they come together, stick, and then continue with a common velocity. So that could be one sitting still, one coming in, connect and hold. It could be coming in together, stick and hold, and then moving in one direction. But somehow they stick and fully hold perfectly. So a perfectly inelastic collision looks something like this. 2 objects approach and collide, one coming this way, one coming this way, or going the same way. They stick, they smush. They're now one object with a combined mass and a combined final velocity. All right. So a perfectly inelastic collision of railroad cars. In assembling a train from several railroad cars, 2 of the cars with masses 2 times 10 to the 4th and 4 times 10 to the 4th kilograms are rolled towards each other. When they meet, they couple and stick together. So this is going to be a fully inelastic collision. The lighter car has an initial speed of 1.5 meters per second. The collision causes it to reverse direction. Okay, so that's negative 0.25 meters per second. What was the initial speed of the heavier car? Okay, so I'm going to set this one up as the mass of the first one initially times the velocity of the first one initially plus the mass of the second object initially times the velocity of the second object initially is going to be equal to their combined masses. So I'm going to call that mass 1 plus mass 2 times their final velocity, okay? Because they share the final velocity and now they share the masses. So I have a conservation of momentum, and this side, this first side over here is all initial. The second side over here is all final. So now I think I can plug in and solve. All right, so 2 times 10 to the 4th is 20,000. 4 times 10 to the 4th is 40,000. I'm just going to plug in those numbers to keep things a little bit easier. So the mass of the first object, 20,000, kilograms times the velocity, the lighter car has an initial speed of 1.5 meters per second, okay? Plus the mass of the second car is 40,000 kilograms times its velocity, which we don't know, the initial speed of the heavier car, that's what we're solving for, equals the mass of both of them together, 20 plus 40,000 is 60,000 kilograms times the final velocity, which is negative 0.25 meters per second. Okay, so 20,000 times 1.5 is 30,000. 60,000 times -1/4 is -15,000 equals, let's see, plus 40,000 V2. So I'm going to have to subtract 30,000 from both sides, minus 30,000. Go away, and I end up with 40,000 V2 equals -45,000. Divide both sides by 40,000. So that's 45 divided by 40, or 1.125. So my initial velocity of the second car is -1.1, and it's all in 2 digits, so 1.125, but we'll leave that part out, meters per second. So the initial speed of the heavier car was 1.1 meters per second, because the initial part doesn't matter, or sorry, the speed part says that the direction doesn't matter. So it'd be 1.1 meters per second. Lovely. Let's stop and think. The two particles shown collide and stick together. After the collision, the combined particles do what? Stop and think. Pause if you need to. All right, welcome back. So I have 0.4 times 2.5, 1.5 times 0.8, and the question is, which way are they going to go? So basically, this one's just looking at which set is bigger. Is that set bigger, or is that set bigger? This one is twice as large, and 1.5 is more than half of that, right? Half of 1.5 times 2 is 3, and that's less than that. So they should end up going that way at the end, because momentum will be conserved. The total momentum would be the momentum on this side plus the momentum on this side, and that'll end up with a net that direction. And that is to the left. So they will move to the left. You could do it with the full math, 0.4 times 2.5, 1.5 times 0.8, see which one's bigger. This one will be bigger, and that'll be to the left. All right, let's analyze a peregrine falcon strike. Ooh. Peregrine falcons often grab their prey from above, while both falcon and prey are in flight. A falcon, flying at 18 meters per second, swoops down at a 45-degree angle from behind a pigeon, flying horizontally at 9 meters per second. Falcon has a mass of 0.8 kilograms, pigeon has a mass of 0.36 kilograms. What are the speed and direction of the falcon now holding the pigeon immediately after impact? Okay, so they stick and hold together, so this one's inelastic. So I can treat their masses and their combined velocities at the end. Now, I need to pay attention because the falcon has a 45-degree angle. So he or she is going to have both vertical and horizontal components. So I'm going to start by just figuring out those vertical and horizontal components of the falcon. Mass doesn't matter, but velocity does. So for velocity, Falcon's coming in at 18 meters per second. Okay, and it's at a 45-degree angle. right? 45 degrees, 18 meters per second. And now I need to know both sides. What is the vertical side? So what's velocity y and what's velocity in the x direction of the Falcon? 45, so then the opposite, well, it doesn't matter, it's a 45-degree angle, so sine and cosine are both going to be root 2 over 2, but we'll do it right anyway, is 18 times opposite over hypotenuse is sine of 45. V sub y is going to be 18 cosine of 45. I won't write that out, but let's see, 18 sine 45, 12.7 meters per second, and y is also 12.7 meters per second, because sine of 45 and cosine of 45 are the same value. So now a peregrine falcon flying at 18 swoops down behind a pigeon flying horizontally at 9 meters per second. So let's do the horizontal part first. It's coming from behind, so the pigeon is going forwards and the falcon is going forwards, so we can add those two together. So horizontally, it would be, so this is horizontal side, the mass of the falcon. I don't want to use F for falcon because that's the same. So I'm going to say mass of the peregrine falcon times the velocity of the peregrine falcon. Oh, but P is for pigeon. Dang it. I wanted to use F for final. How about raptor? R for raptor. Okay, peregrine falcon is a raptor bird. So the mass of the raptor times the velocity of the raptor plus the mass of the pigeon times the velocity of the pigeon will equal the mass total, velocity total after they are caught. Okay, so the mass of the raptor is 0.8 kilograms, excuse me, times its velocity. So this is just the horizontal component, right? So the horizontal component is just the x component, which would be 12.7 meters per second, plus the mass of the pigeon is 0.36 kilograms. The velocity of the pigeon, it is going 9 meters per second, equals the total mass would be 0.8 plus 0.36, which is 1.16 kilograms, times their horizontal velocity. Okay? So velocity x. I said t, but this is the x component now. So let's do the math on that one. 0.8 times 12.7 plus 0.36 times 9, 13.4 divided by 1.16, 11.55 meters per second. Yeah, that makes sense. Yeah, okay. Because it's between the two speeds. I was thinking you could add the speeds together, but that's not right, right? They're both coming in close to the same speed. When they collide, the raptor will slightly accelerate it, but for the most part, it can't go faster than the raptor was coming in ahead of time, right? They're not crashing into each other and sending one off, so that makes sense. 11.55 or 11.6. So V sub x is 11.6 meters per second. Okay, now vertically, the pigeon has no vertical acceleration. It had, no vertical momentum. It's just going horizontally. So for vertical, which is the y component, it's just the raptor. So I'm going to ignore the pigeon altogether. It'll be the mass of the raptor, velocity of the raptor at the beginning, plus 0, which is the pigeon, equals the mass total times the final y velocity. Okay? So that is 0.8 kilograms times the y component is 12.7 meters per second equals the total mass 1.16 kilograms times the y component, 0.8 times 12.7 divided by 1.16, 8.76, or v sub y equals 8.8. I'll do 7.6, whatever. 7.6, yeah. Meters per second. Okay, so I've got the x component and I've got the y component. Now I can put them together to find the total. And this is going to be another diagram, another triangle. So my x component was this way, right, at 11.6. And then my y component was going down because the Falcon was coming down at 8.76. So the question is, what is the total, right? What is my final velocity and what is that angle? So let's do the final velocity first. So that's an a squared, b squared, c squared for me. V squared is equal to 11.6 squared plus 8.76 squared. V equals, do the math really quick, 11.6 squared, boom, square root, 14.5. So my velocity is a grand total of 14.5 meters per second. And then the last part is what about the angle? So for the angle, I can do the tangent of theta, because I have the opposite and the adjacent, equals 8.76 over 11.6. And then I have to do the tangent to the -1, the inverse tangent. It's the second part of the tangent button. So tangent to the -1 of 8.76 over 11.6 gives me 37 degrees. So that angle, theta, is equal to 37 degrees, and that is below horizontal, right? Because I have a greater horizontal component, so that would be below horizontal. So the Falcon plus the pigeon, after the pigeon is grabbed, will be moving at 14.5 meters per second, 37 degrees below the horizontal. So, choo, just like that. Awesome. That's looking pretty good. Nice. And that takes us back up for one more concept, which is angular momentum. Okay, so angular momentum is a little bit tricky because we haven't learned about rotational inertia yet. Just like in energy, they introduce some angular stuff, and the textbook introduces it in a different order than the AP class does. So I'm going to introduce it, and it'll make more sense in another unit or so. So angular momentum, L, is equal to the moment of inertia times the angular velocity. And you'll remember from energy, angular velocity is in radians per second. Moment of inertia is kilograms meters squared. So there's this nice little table just kind of showing that rotational dynamics and linear dynamics have equivalents. So like torque is effectively equal to force. Torque in a circle is force. Moment of inertia in a circle is equivalent to the mass. Angular velocity is equivalent to linear velocity. Angular momentum, L equals IW, is equal to linear momentum, P equals MV. Okay. Then there's also this idea that if we do some fancy math and turn I into its thing and angular velocity into its components, then I can get that L equals mRv. So that's the mass times the radius of the circle times the velocity of the object going around the circle. Linear velocity of the object. Okay. So analyzing a spinning ice skater. So I also have two other pieces that I, or the moment of inertia, is equal to m, the mass of the object, times the radius squared. Or if it's a solid disk, so this would be a solid disk, then it's equal to 1/2 the mass of the disk times the radius of the disk squared. So those are also helpful for inertia, moment of inertia there. And then angular velocity is just radians per second. Since radians per second is like 2 pi radians in a rotation or a revolution, then we could also say, you know, another potentially helpful one is that, oh, that should be loopy, funny looking W, angular velocity, equals 2 pi times the frequency, would be another way of expressing angular velocity. 2 pi radians times the frequency, number of spins per second. Okay, so for the ice skater, an ice skater spins around on the tips of his blades while holding 5 kilogram weight in each hand. He begins with his arms straight out from his body and his hands 140 centimeters apart. While spinning at 2 revolutions per second, he pulls the weights in and holds them 50 centimeters apart against his shoulders. If we neglect the mass of the skater, how fast is he spinning after pulling the weights in? Okay, so I want how fast is he spinning, and that would be in revolutions per second. So I think I'm going to have to do a conservation of momentum one here. So I'm going to have to do conservation of momentum before versus conservation of momentum afterwards. I'm going to ignore the skater himself and just pay attention to the weights. And that's a fair approximation because you are pretty much symmetrical on either side of your body. So we can kind of say that your two sides are equal and it should kind of balance out. All right. So I'm going to say that the initial momentum is equal to the final momentum, or IW at the beginning equals I, funny looking W at the end. Now, this is two objects that are not a disk, right? They're on the outside, so it's going to be mr squared, but there's two of them, right? Two of those objects. So the I part is going to be the two objects, so 2 of the mass times the radius squared times W, and W is revs per second, which is 2 pi times the frequency, okay? So 2 pi times the frequency equals, oops, got to convert this one too, and this would all be initial. All right, so this one is initial is equal to, same deal, 2mr squared times 2 pi frequency, and this part would be the final part, right, after he brings them in. Okay, so let's kind of cancel everything that I can cancel and see what happens. Let's see, so when I'm canceling things, I could say the 2 is going to cancel the 2. The 2 pi is going to cancel the 2 pi. The mass remains the same, right? They're both 5 kilogram masses, so the mass doesn't change. What's changing is the radius and the frequency. So if my original radius was 140 centimeters, so that's radius is 1.4 meters squared times my initial frequency was 2 revs per second equals my final radius is 0.5 meters squared times my final frequency. Okay, so let's try that. 1.4 squared times 2 divided by 0.5 squared, 15.68, or frequency is 15.68, approximately 16 revolutions per second. Meters squared cancels, and I'm left with revolutions per second. So my total frequency there is 16 revolutions per second. He's gone 8 times faster by pulling the weights in. And you'll see that if you're watching figure skating on the Olympics, or not the Olympics since those were delayed. Summer Olympics, Winter Olympics, still going for 2022, I think. So if you watch figure skating not in the Olympics until 2022, and you see them like tuck in, they'll start spinning really, really fast. This is also like why gymnasts, if they're doing flips, they tuck in really tight. And then when you're ready to land, you fully extend out, right? And by fully extending out, you change how big your moment of inertia is, and that slows you down, and then you can land straight. Same deal for divers. Tuck in tight, spin, 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 open up, land, no splash. Perfect. But gosh, getting a gold medal in the Olympics is so easy when you know physics. Okay. Last stop and think. The left figure shows 2 boys of equal mass standing halfway to the edge on a turntable that is freely rotating at angular speed, funny WI. They then walk to the positions shown in the right figure. The final angular speed, funny WF, is, okay, so I know that the angular momentum has to be conserved. So I've changed my moment of inertia. And the moment of inertia, the disk has stayed the same. The thing that's changed is the 2 boys. So I'm looking at mr squared. In this case, I have 2 of them that each have, well, the masses haven't changed, right? So I have 2 of them that each have a mass. So I got 2 times the mass. I'm gonna call that a regular radius, right? Mr squared, okay? In this one of them is in the center, so he has a mass, or he has a radius of 0. The other one is all the way on the outside, so he's gone for 1 m, but now he has 2 radius squared. So his radius has gotten bigger, right? 2 squared is 4, so this would be 4 mr squared. So this one out here has a bigger I, a bigger moment of inertia, which means this one has a smaller I, right? I is smaller. This one, I is bigger. And if L has to equal L, and L equals WI, WI, or IW, got those backwards. As this I gets bigger, this W has to get smaller. So the final should get smaller. The final angular velocity should be less than W sub I. All right, last one looks like a real challenge. Let's see. It's about aerial firefighting. How relevant? A forest fire is easiest to attack when it's just getting started. In remote locations, this often means using airplanes to rapidly deliver large quantities of water and fire suppressant to the blaze. Just as a side note, those pictures of the super big planes that drop the red fire retardant, super cool looking. The Super Scooper, that's a great name, is an amphibious aircraft that can pick up a 6,000 kilogram load of water by skimming over the surface of a river or lake and scooping water directly into its storage tanks. As it approaches the water's surface at a speed of 35 meters per second, an empty Super Scooper has a mass of 13,000 kilograms. It takes the plane 12 seconds to pick up a full load of water. If we ignore the force on the plane due to the thrust of its propellers, what is its speed immediately after picking up the water? Okay, so the speed of the plane is going to be it's changing its mass. It has let's say the impulse we'll get to later. So right now it's just a change of momentum problem, right? Change of momentum, change of momentum. I don't think that the time is actually necessary right now. I think that we just say it's a change of speed based off of the change of mass. Okay, so I'm going to start for part A by saying mass initial, velocity initial equals mass final, velocity final. The initial mass was 13,000 kilograms times the initial velocity, 35 meters per second, equals the final mass is the 13,000 plus the full 6,000, so 13 and 6 is 19,000 kilograms times the final velocity. Solve for final velocity and get a little bit of quick math. 13 times 35 divided by 19, 23.95. We'll round that to 24 meters per second. Okay, nice. What is the impulse delivered to the plane by the water? Okay, so the impulse is going to be force times time, and that's equal to the change of momentum. So let's see, the change of momentum would be the plane's change of velocity. Yeah, we're ignoring the water. We're ignoring the water is what's delivering the impulse. So, okay, I think I got it. I got to kind of think through these ones. So for part B, I know that the impulse is equal to the change of momentum, which is equal to the mass of the plane times the change of velocity, which would be velocity final minus velocity initial. Plug in numbers there, equals the mass of the plane was 13,000 kilograms. Final velocity was 24 meters per second minus initial velocity, 35 meters per second. That's a net change of negative 11. Let's see, minus 35 times 13, 1, 2, 3, negative 143,684,000. I used the value of 23.95 that was already in there. But since I'm rounding to 2 digits, that would be negative 140 J equals negative 140,000 newtons times seconds. Okay. All right, looks good. And then part C, what is the average force of the water on the plane? Okay, this is a nice easy one. J equals force average change of T, negative 140,000 Newton seconds equals force average times 12 seconds. Divide both sides by 12. Negative 12,000. Okay. So that would be force average equals negative 12,000 newtons. Okay. And then finally, part D, the plane then flies over the fire zone at 40 meters per second. It releases water by opening doors in the belly of the plane, allowing the water to fall straight down with respect to the plane. What is the plane's speed after dropping the water if it takes 5 seconds to do so? Oh, okay, it's another change of momentum one, right? So the horizontal momentum, oh, you know what? This is going to be tricky. Okay, so before you have plane, beautiful drawing, good. Plane plus water, right? This is before. After the drop, I have plane plus water. The water is below the plane, but it's still going. There we go. At the beginning, the plane and the water were going 40 meters per second. Afterwards, the plane and the water are still, the water is still going 40 meters per second, and the plane is still going 40 meters per second, assuming no air resistance. So, has there been any change of speed? No change of speed, because everything is still moving horizontally. They've separated vertically, but horizontally, because it says it falls straight down with respect to the plane, there is no change of speed. So the plane is still going 40 meters per second. Boom. All right. So with that, we are now ready to hit those practice problems, all multiples of 5 questions and problems. Best of luck. Have fun.